Oh. Okay, well now it's over there. Now it's over there. I guess it's a delay. Oh, it's looking for me. Like worst. That's weird. All right, should I start or? All right.
All right, so welcome to the second lecture of Henrik, also known as the J from BCJ.
Okay, thanks. All right, so yesterday we talked about color. And we also talked about kinematics. Oof. Maybe I used the other chalk. And how to sort of relate them. And basically what we did is that we talked about the fact that if you just consider all color factors built out of FABCs, then there were, if I denote this as the number of them, there was 2n minus 5 double factorial. And then we used the Jacobi identity to reduce it to our half-ladder color factors, of which there are only n minus 2 factorial. And then we talked about, for the kinematics, you start with, for example, maybe the color-ordered amplitude that David also talked about today. Which you can just label by some ordering, and then you consider all other permutations as well. That will give you a set of amplitudes, and I guess we didn't count them exactly, but I guess David did it today. It's n minus 1 factorial over 2. That's basically modding out by cyclicity and reversal symmetry. But then we said that this was actually part of a bigger set of identities, which are the Kleist-Coif relations, and that takes you down to the also like the half-ladder basis you can call, or DDM basis is what people typically call it, DDM. And the number of such was also n minus 2 and factorial, and thus we have the same number of color factors as partial amplitudes, which are independent. Then we say that these Kleist-Coif relations are a bit mysterious, and we could make it more less mysterious if we introduce numerators, or basically diagrams. Right. Basically diagrams of the form numerator over denominator, and there was some plus minus sign here, depending on which, well, how you represent things. And the number of such thing is of course also the same as the number of cubic diagrams, so that's 2n minus 5 double factorial. So we made the KK relations manifest. At the price of introducing this diagram, numerator over denominator diagrams. But the problem, of course, is now we have spoiled this nice analogy that we always have equally many color factors and kinematic factors. And now we have this many again, so we have to basically repeat the procedure. So problem, too many too many NI, too many kinematic building blocks. And there's another problem, is that there's actually more relations. We use the Kleist-Coif relations, but this actually does not exhaust the number of relations, so there's more relations. So that's what we're going to talk about today. Okay, so this n minus 2 factorial I don't know what to call it, KK or DDM or half ladder. this basis is always, this basis always exists if you're working with only adjoint particles at tree level. So this works. So this basis A1 sigma n, sigma is the permutation. It works in generic gauge theory. Or all gauge theories that have adjoint particles, adjoint representation particles, such as pure Young-Mills, for example, only has gluons, all in the joint. But all other particles that you put in the joint, this basis exist. But there are also other relations, so which hold for some or many. So many gauge theories have a smaller basis. And this is due to the fact that there are more relations, which I'm going to call BCGA amplitude relations. Sometimes I just call BCA relations, but it's useful to put the word amplitude there because there's also another set of relations which can be confused. And those relations takes you to a smaller basis, which is n minus 3 factorial. And let me give it here. Let me give you the needed relation. So it looks very similar to how this U1 or photon decoupling identity look like, in the sense that let's see what happened to my yellow. In the sense we pick one particle. One particle is being special. Let's pick it to be particle 1. And then the other particles are not special. So let's just denote it like this. But we multiply it with a prefactor. So in particular, it's going to be P1.P1. You might say that's 0, but don't worry about it. Then we multiply by P1.P12. And then we write down the amplitude where we have moved particle 1. So now particle 1 is the second location. Then we add more terms, so it's P1 dot P1 to 3, A 2 3 1 dot 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 all the way to n. And then there's a bunch of more such terms until you reach the last one, A 2 3 dot dot dot. And I guess we put it right before the last leg. So 1 and n. And the factor here is P1 dot P1 2 dot dot dot. N minus 1. So the claim is that this is 0. And P1, 2, 3, dot, dot, dot. It's just the sum of the momenta, P1 plus P2 plus P3, Pn. Okay, yeah, so basically you move leg 1 around, and each time you have written down an amplitude, you take all the momenta to the left of leg 1, and you write down that momenta and dot it into P1. Obviously, P1 dot P1 is 0, so you could have not included P1 here or whatever. But I do it for the formula is slightly prettier. Okay, so it turns out that this is the relation you need, plus all permutations of this relation, right? You can basically permute your n particles, and that gives you a sufficient number of equations to go down from n-2 to n-3. And I'm not going to show that that's what happened, but you just have to believe me that that's what's happened. And in fact, this is, to connect to David's talk, this is what he was referring to, bonus relations. So there are some parallel talk in the literature about bonus relations, but I guess they were never written down. And then later on, in hindsight, it was realized that these are also the bonus relations. But okay, so the non-trivial claim that I want to do here, so non-trivial claim is that this BCA relations comes from imposing Color-Kinematics Duality. So we already sort of started imposing Color-Kinematics Duality here by aligning color factors and kinematic factors, and then we obtain these numerators, and we have too many numerators, so we need to reduce them in the same way as we reduced the number of color factors, basically using the Jacobi identity. So, for every Jacobi identity, color Jacobi identity, which takes this form, something like that, equal to 0. And the reason I put plus minus here is because, as I said, you can always redefine your color factors, so sometimes it's a bit unclear which sign you should pick. So you might end up with various different signs depending on your conventions. But you pick some convention, and you get some Jacobi relation, which is a 3-term relation, either with pluses and or minuses. And then you impose a kinematic version of this identity. Which is basically going to look the same way, but now with numerators. And it's important here that if you have some particular sign convention here, you pick the same sign convention over there. So they have to be 1-to-1. And of course, at the end of the day, you're going to multiply these things in the amplitude, so that's why this sign is kind of arbitrary. And pictorially, I guess it looks the same way as before, that you have some diagram. And this diagram, to be clear, this diagram doesn't need to be 4-point. It can be some higher points. So let me indicate it like this, that this could be some part of some larger diagram. And then you add to it, well, let me see so I get my signs correct. I guess in this particular convention, I'm going to get, I guess, minus actually. Minus this guy, which also is part of some larger diagram. And I guess the other one is also going to be minus. Where did it go? So it's this one. So it's often easy, and then you want this to be 0, I guess. Yeah. So the reason why we do this pictorially is that we want to do it kind of abstractly, so we can do it with numerators, but they're a little bit too abstract. So then it's sometimes more convenient to just draw the diagrams like this. Okay. So basically, I now sort of want to try to demonstrate this non-trivial claim and see how it works. So I guess we're going to consider 4 points. Maybe I go over here. So consider 4 points. I think we already talked about it last time, but I guess this will be a slight recap. So here we have our color-dressed amplitude, full amplitude at 4 point. And we can write it now as a sum over some S-channel numerator, S-channel color factor, and then the pole term, which is 1 over S. And then likewise, NT CT over the T channel plus NU CU over the U channel. So that's roughly how we write down our amplitude. And then I can say that our color factors, let me just give it in the S channel. So the S channel color factor is just FA1, A2, B, FB, A3, A4. And then CT is actually just a permutation of the above, so we can just write it as 1 goes to 2, 2 goes to 3, 3 goes to 1, and CU is also a permutation of the above, so basically CS, and then 1 goes to 3, 2 goes to 1, 3 goes to 2. Just a cyclic permutation. And then now here I basically fixed my sign convention. So in this sign conventions, the Jacobian entity looks as follows. It's just the sum CS plus CT plus CU is equal to 0. Okay, and then the kinematic. The kinematic Jacobian entity is then, of course, the same. Now, whether this identity exists or not, that's a different question. Then you actually have to go to a specific series and try to see if it can be realized there. But for now, let's assume that it does exist, and then see what the consequence is, right? So in particular here, you can solve this one. And by solving, I just mean decide which one to eliminate. So we can, for example, eliminate the T color factor. So we can write it as minus CS minus CU. And likewise, NT is equal to minus NS minus NU. And then if we do that, our amplitude becomes the following: NS over S minus NT over T. So I start by eliminating the color, but I keep the numerators as they are. So this is just the first step. Okay, so here I've eliminated the color factor CT, and that's why I only have 2 color factors left. And basically the T-pole, the T channel has now moved into these brackets here. Okay, and then The next step is to also eliminate NT, and then you basically get a matrix. So let's call it, let's have a row vector here. Then we have a matrix, 1 over S plus 1 over T, 1 over T, 1 over T, 1 over U plus 1 over T, multiplied by a column vector NS and T. Okay, so I basically eliminated both the T-channel color factor and the T-channel numerator, and I got this matrix representation of our amplitude. You might wonder why do I care about that matrix representation? Yes? Say again? Did I make a typo? Oh yeah, sorry, yes. Oh, that's a crappy one. Yes. Okay. Yeah, so essentially what I want to do is I want to turn this into a homework problem. But I kind of already done part of it, but let me still say that this is a homework. So basically the homework here is repeat sorry, where did I go? Repeat the 4-point exercise that I just did and arrive at a formula for the partial amplitudes. So now I have partial amplitudes in a column vector instead. So if we put the partial amplitude in a column vector, we can then write like a matrix equation in terms of the numerators. And this matrix is essentially this matrix, but I have inserted some signs. So let me just write it down again. So this part is the same, but in the lower row here, I have inserted a minus sign. So that's a comma there, 1 over U. Okay, so I guess I want you to repeat what I did and then also identify the partial amplitudes such that you get this equation instead. So identify and here, right. And let us also give this a name. So I guess this is what we called before 1 sigma 4, where sigma is a permutation. You see that it's exactly the 2 permutations of 2 and 3. And here we can also represent this as a numerator 1 row, comma 4. And this matrix here, people typically call it M sigma row. And obviously there's a sum here over row. Okay, so the first part of the homework, arrive at that equation, then confirm that the determinant of this matrix is actually 0. So the determinant of M sigma rho is actually equal to 0. And given that it's 0, it implies that there's a relation of this type. All right, so is it clear what to do? Do what I did there, and then arrive at this formula, confirm that the determinant is 0, and then show that given that the determinant is 0, this equation must hold. And this, of course, is the simplest BCA relation. This is the BCA relation at 4 point. This is the only, well, sorry, it's not the only one, but in this space, this is the only one, but then, of course, you can do permutations. Okay? And you're welcome to repeat it at 5 point, but I'm not going to assign that as a homework because that's usually more intense. Okay? But you can, in principle, repeat this exercise at multiplicity n. Yeah, and I should apologize for using the letter n both for the number of particles and the numerator. It's just accidentally we did that, and I guess we're stuck with it. It should be clear from the context. But anyhow, so go to multiplicity n now. And then you can show that the Jacobi, using the Jacobi identity, this takes you down to n minus 2 factorial basis of numerators. Well, that's not hard to understand because that was true for the, well, I erased it, but that was true for the color factors. And so we've just imposed the same algebraic relations for the numerators. Of course, you have to go to the same basis. And then we can write our partial amplitude as follows. M sigma rho n 1. Okay, so here is kind of obvious that there's a flaw in my notation. This is the number of particles, this is the numerator. And rho here is a permutation which runs over the permutation group Sn minus 2. So basically, permutations of n minus 2 particles. Okay? And I should say that this matrix here has many names. I think in some early work it was called propagator, propagator matrix. Basically because it's a bunch of propagators. It's not that each entry is a propagator, but each entry is a sum of propagators. But it's also can be identified with amplitudes in a particular theory. So sometimes people call it biadjoint scalar amplitudes. Obviously, if you just look at these propagators, it looks like propagators of a scalar theory. And so that's why there's this identification. I will actually explain that later on, but for now, just take it as a name. And then the claim here is that if you repeat this exercise, you can work out that the rank, the matrix rank of this matrix, the propagator matrix or the biadjoint scalar amplitude matrix, is n minus 3 factorial. So is a n minus 2 factorial by n minus 2 factorial matrix, but only n minus 3 factorial of the entries are independent. Yeah, so let me write that here. It's a n minus 2 factorial by n minus 2 factorial matrix. So it's a pretty large matrix, but it has a quite large null space. And that's basically the fact that there is a null space there is the same thing as finding relations between the partial amplitudes, which are the BCA relations. Why is it that this matrix is generate? So let me try to make an argument why that's true. So why is this matrix degenerate? Well, let me answer in the following way. If it wasn't, or if it were not degenerate, then it's invertible. Then it becomes invertible. And numerators can be uniquely solved. Solved in terms of the partial amplitudes of gauge invariant partial amplitudes. And that's bad because that contradicts some basic facts that we know about Feynman diagrams. And we know that Feynman diagrams are not gauge invariant. So this contradicts the gauge, well, let me say gauge symmetry principles. You shouldn't be able to uniquely pin down numerators of Feynman diagrams. Well, we don't know if these objects are Feynman diagrams, but if we assume that there are Feynman diagrams, then you shouldn't be able to invert this matrix to get the numerators as a function of the partial amplitudes. So maybe it's not an explanation, but it kind of makes sense that there should be something like that. And thus I think the final conclusion here is that the BCA relation they follow from Color-Kinematics Duality, but also from gauge invariance principle, right? If you didn't have the gauge invariance argument, it's kind of hard to argue why this should be why it should be a degenerate matrix. In fact, there are some cases where you can work with particular amplitudes. For example, if you have matter on your external legs, for example, if you have fermions maybe on your external legs, you can repeat the exercise. You can change some of the details, and then you land on a slightly different propagator matrix. Let's say if you have flavor, and then it turns out that it's actually invertible. But that's not a contradiction, right? Because if you have external fermions on all of your legs, then there's no gauge invariance, right? It's just gauge invariance from the start. That said, maybe this is not fully satisfactory because there's also theories which I will talk about shortly. For example, this bi-adjoint scalar theory. It also has no gauge symmetry, but it does have BCA relations. So, but usually if you ask me why do they exist, it's because of color-kinematics duality and gauge invariance, but there could also be alternative explanations. All right, any questions? Yep. Well, I say that I would, in general, I would say that there are no BCA relations at loop level. However, people have written down BCA relation at loop level. In particular, one loop have written down certain relations, I believe at least. But I would say that they're mostly a property at tree level. And then if you happen to maybe be able to implement some of it at loop level, it's because you can relate it directly to tree level. Basically, you can take this forward limit at one loop, and then you can write your loop as a sum over tree level contributions. So I think it's more of an accident if you find similar BCA relations at loop level. Also, they would not be very useful. So at tree level, it can be useful because you just have fewer partial amplitudes to work with. But the price you pay is that if you try to actually solve, like if you try to solve this equation, you see that you will get an S downstairs, right? So typically you will have stuff in the denominator. So if you just go to a reduced basis of partial amplitudes, it will have all sort of denominator factors which may or may not be physical, depending on which color order you're in, right? So at loop level, the problem would be that if you repeat that loop level, you will get various kind of crap in the denominator, which you don't want to do in general, because it might be hard to integrate. Anyhow, I hope that answered the question, yeah. All right, so I think gauge invariance is quite important in the story, so let me talk about it a bit more. All right, so let's talk about gauge invariance. Whoops. Yeah, so in some sense, this whole program of writing down BCA numerators, making color kinematics duality manifest is sort of against the philosophy in the amplitudes program, because in the amplitudes program, you want to talk about only gauge invariant things from the get-go. You don't want to talk about Feynman diagrams. You don't want to do a lot of things that you do here, but there is as I said in the beginning of lecture yesterday, color kinematics duality was discovered for on-shell processes, but it really wants to live off-shell. So it really wants to talk about the same thing that you can talk about off-shell. So with the numerators, we lost manifest gauge invariance. Because they are not gauge invariant, so we lost it. But we gained something else. So basically, we gained the power of the gauge invariance principle, or gauge transformation, or I guess worded than this. So this means that we can now consider how our numerators behave under a gauge transformation. So you might know that if you do a gauge transformation on an external gluon, the basic consequence is that you just shift your polarization vector by something proportional to momenta. You can make it some arbitrary factor here. Typically, you consider this to be a small quantity, but it doesn't really matter. So let's just shift my polarization vector with momenta. And of course, what's going to happen if I do that for my numerators? Well, I know that my numerators are going to be a linear function of the polarization vector. That's true in a gauge theory. So then I would expect that my numerator should then also transform with some kind of shift. Let's just call it delta I. So basically, my numerator just shift by some functions, a set of functions, delta I. And then if I consider the color dressed, or the full amplitude, so this can be at n points. Let me just write it schematically. Well, so yeah, let me not write n because it's confusing. But basically, my color dressed amplitude is just a sum of cubic diagrams, or graphs, and then it has color factors, numerators, and denominators. So that's before transforming it. After transforming it, it becomes itself plus this contribution from the shift, which is basically sum over I, Ci delta I over di. So the claim here is this contribution has to be 0. And I'm not using any special property, like I'm not using Color-Kinematics Duality here. I'm just using the fact that if I have a gauge theory amplitude, I should be able to write it on this form, where I have basically absorbed all the quartic interactions into the cubic interactions. You can always do that. And then if I do the gauge transformation, it will transform like this. But we know that if it's a sensible gauge theory amplitude, it should be gauge invariant. So this quantity here has to be 0. But why is it 0? Well, it's 0 because, well, first of all, the delta i's might have some special form, but it's also 0 because these color factors here are actually not independent, right? So if the color factors here were independent, then it could only be 0 if delta I is 0. But we also know that delta I cannot be 0 because that would contradict numerators being transforming under gauge transformation, right? So the only way it can be 0 is because we are working in a overcomplete basis of n minus 2n minus 5 double factorial. That's basically the number of cubic diagrams. So this goes from 1 to 2n minus 5 double factorial. And that's an overcomplete basis, and that's the reason why you get this crap here, which doesn't want to be 0 manifestly, right? It's only 0 after some non-trivial work. Yeah, so this is 0. So this vanish, that's right here. Vanish due to Jacobi identities. Of the color factor of Ci. And this is essentially, this is one reason why, if you have a gauge theory, the color factors has to live in a Lie algebra, so there has to be Jacobi identities, and you have to get 0 here. So I'm just asserting that as a fact, because otherwise, everything we know about gauge theories are wrong, so this has to be a fact. Okay, and why am I mentioning that? Well, because this property is something I'm going to recycle in a slightly different context. So now what we're going to do, well, we're going to basically do what we call double copy. So introduce a second copy of numerators, or second set, maybe is a better word, and let's call them n twiddle, that also obeys Color-Kinematics Duality. Meaning that the Ni twiddle are basically dual to the color factors. Whoops, no tilde there. And then since they are dual in the sense that they obey exactly the same identities, we can actually swap color for numerator. So let's do that in our partial amplitude. So just take the color factors and swap them out for this n twiddle. So that gives us a new object, and this new object I'm just going to call M. I guess curly M. Well, I don't know if it's curly or not. But it's going to be a sum. Well, let's make it curly, I guess. So it's going to be a sum over two copies of numerators, n and n tilde. It still has the same denominators, and it's still the same sum. Let me just write 1 to 2n minus 5 double factorial. And just as David in his talk yesterday, he was saying that there's some issues with dimensional analysis, so you have to make up for that. And so you can basically divide by a mass here if you want, but traditionally we just multiply by kappa, and kappa is a quantity which scales like 1 over mass to make up for the fact that the dimensions are a bit wrong. But yeah, this is the double copy. At least at 3 level. And because what we were just arguing over here, this amplitude, whatever this is, will inherit similar properties as the gauge theory amplitude. So this is also going to be invariant. Under gauge transformation, where Ni goes to Ni plus delta I. So let's just say we're transforming just the Ni's, never mind what happens to the Ni twiddle. And then you can work out that indeed this capital M will transform to itself plus sum over Ni twiddle delta I over di. But this thing here is equal to 0 because we just said that the numerators here, n tilde, satisfy exactly the same relation, same algebraic properties as the CI's. So therefore, if this was 0 because of the properties of CI, this has to be 0 by the same property. And it's the same delta I. So if there was some magic due to delta I, the same magic is going to happen here, right? So this is 0 by the kinematic Jacobi identity. Okay. All right, so what did we just show? We showed that there was gauge invariant, and we showed that there was gauge invariant if you transform a polarization vector. But you might realize that there are actually 2 polarization vectors in this formula, and we just transformed one of them. But of course, this n twiddle also contains its own polarization vectors in general. So you can also consider the case where you shift those guys, and again you will recover the same cancellation, but just swapping n and then tilde. So essentially what that means is that you should also make sure that the n's satisfies color-kinematics duality if you want something gauge invariant. Okay, but so what we have essentially showed here is that this m is actually a gravitational amplitude. So m is a gravitational amplitude. Why? Because first of all, if we have two copies of polarization vectors, then it actually contains spin 2 particles, or polarization. So you can always write the polarization tensor as an outer product of two polarization vectors. So you can always do that if these polarization vectors are null. Because then, if they are null, then this graviton polarization will be traceless, which is what you want of a graviton polarization. So for example, if you're in 4-dimension, you can always choose circular polarization, and then they're going to be null. Okay, so we just argue that whatever the amplitude contained, it contained spin 2 polarizations. It also contains two derivative interactions. Two derivative interactions. How do we know that? Well, it turns out that if you start from, say, a normal gauge theory like Yang-Mills, then you might know that when you compute your Feynman diagram, that you basically insert one momenta here, which I can just think of as a derivative, and you insert one momenta there in that vertex. And then, of course, what you're going to do in the double copy, you're basically going to square the numerator, never mind the propagator. We just square the numerator. But now, basically, what we've done is that we have essentially squared the number of derivatives in each vertex. And you can show that if you have some kind of contact vertex or whatever that would result from this procedure, that would also be two derivative interactions. So everything's going to be two derivative interactions, which is the correct number of derivatives in a gravitational theory. And then lastly, what we showed over there is that it has a gauge symmetry, and that gauge symmetry is, of course, called diffeomorphism symmetry, or this is a diffeomorphism invariant. Amplitude. And the reason for that is that essentially what we did there, you can just think of as the following replacement. We take the graviton polarization tensor, and then we shift it. Something proportional to momenta, and then a polarization vector, and then you symmetrize it. We didn't do it in a symmetric way, we did it in an asymmetric way over there, but you can convince yourself that if you shift both n and then tilde, it's more or less the same as doing a symmetric combination. And this momentum here is basically just the momentum over here. And then we still have one polarization. You might be worried, but what if you shift both polarizations? Shouldn't we have something like two momenta here, like two p's? And the answer is no, because we have to remember that this shift here is supposed to be a small shift, like an infinitesimal shift. So having two p's would actually be even smaller than infinitesimal. So we don't have that term there. Okay. Any questions? Yeah. Sorry? For gravitational amplitude? Well, it's the same Jacobi identity as we used for gauge theory, right? So it's, what do they mean? I don't know what they mean. They just, I asserting that they exist. I assert that they exist. I mean, proving that they exist is a different story. Maybe I should leave that as a homework. So homework, find NS, NT, and U for pure Young-Mills, such that NS plus NT plus NU is equal to 0. So now what I mean is that, you know, take your favorite representation of pure Young-Mills, like dig out your Feynman rules, and try to massage. Basically, what you have to do is that you have to massage your 4-point vertex into those 3 channels, such that you get 0 when you sum them up. That's a highly non-trivial. Well, it's highly non-trivial to do on a blackboard, so that's why I'm not doing it. But if you do it in Mathematica, it should be fairly easy. Yes? Yep. What, sorry, I showed what? Oh yeah, I showed that you get some gravity. Is that the question? Which gravity is it? Well, yeah, that you, yeah. Well, that's generally a difficult question. Which gravity is it? However, there's a clue here. There's a clue here that there has to be 2 derivative gravity. There's also gravities which have more than 2 derivatives, but we usually don't. Well, sometimes we don't even want to call them gravities. But this is a 2 derivative gravity, so you can then start guessing, you know, how many such gravities are there. And it turns out that there's only one if you have pure graviton theory. So if you ignore matter, there's only one, which is Einstein-Hilbert action. That's the only action you can write down. Well, you can write down lots of stuff, but they're all equivalent to Einstein-Hilbert at 3 level, and if they're 2 derivatives. But you might also worry about whether there's some matter that got polluted into the story. And that's true. There is going to be some matter as well in these amplitudes. However, if you're looking at only external gravitons at 3 level, then you can ignore this pollution. But I will talk about the pollution later on, I guess, yeah. Hmm? Factorization into KLT, you mean, or? Yeah. Yeah. Yes. Yes, yeah, there's a lot of other things you want to test if it's an amplitude, I guess. Yeah, and so I guess I should have made a longer list. So indeed, you want to check factorization properties. Is that what you're talking about? So on the pole, how does it behave on the pole? But the claim is that this guy only has the physical poles, first of all. So you don't have to worry about any unphysical poles. So he has only Feynman diagram poles. Then he has numerators. And yeah, what do we know about these numerators? Well, we know that they have the right factorization properties for a gauge series. So if you're doing Young-Mills, it will have the same factorization properties as Young-Mills by definition, because we just say, we declare that this amplitude should describe our gauge theory, and therefore it will have the right factorization properties by default. How do you know that gravity has the right factorization? Well, then you have to maybe do that recursively, right? You have to start the argument at, start at 3 points. Then you say, yeah, it works at 3 points. Then you have to say 4 points and so on, and you can make a recursive argument out of it. But I don't know. I think that's Yeah, I don't want to do it on the board. I think, yeah. I don't know if that's satisfactory. Yeah. 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 Yeah, then you can also discuss whether it has the right bow symmetry, because that's important, that a graviton should be bow symmetric. It also should not have any kind of flavor or color or whatever. Kind of obvious that we got rid of the color. But yeah, it's also it's going to be totally bow symmetric because of the way we have represented it. So it will have all the right properties, and you can make this list longer. I got tired after 3 bullet points, I guess. Yeah. Yeah, you can try to argue in the reverse direction. Like if you know, if you, yeah. I mean, you could say, let's say, I have written down some amplitudes in gravity. These amplitudes are going to be diffeomorphism invariant. Does this now imply that the numerators should exist, and that they're going to satisfy this property? I think the answer is no. It's not. I think it's not reversible because there's many more ways to write the gravity amplitudes that does not write it as a sum of 3 squares. Or I think maybe at least at 4 point you can probably argue that all ways of writing the 4-point amplitude will implement some factorization, right? But I think once you get to 5 point, there's many other ways to write the gravity amplitude, which not gonna imply the existence of numerators. Yeah. In fact, people have even explored. They have explored what happens if you have numerators do not satisfy Jacobi identities. Can you still write some double copy formula? And the answer is yes, you can, but it's way more complicated, and you don't want to do it that way. Yeah. Yeah. Well, I mean, luckily, the theories we're talking about here, they live in any space-time dimension. So pure Yang-Mills and ordinary GR, they live in any dimension. They're happy to live in any dimension. So there's very little sensitivity on the dimension. Okay, if you go down in dimension, then you're in trouble. So don't go down to 1 or 2 dimensions. That's bad. But they're typically quite insensitive, but there might be other theories which care about the dimension. So yes, so if you're talking about, for example, Chern-Simons theory that only exists in 3 dimensions and so on. Yeah. Yeah. No, I mean, there's lots of accidental identities in various dimensions, but here, basically, what I'm saying, you should just ignore the accidental identities. Just do the ones that exist for any dimension. You might also know when you compute your 3-level gravity amplitudes, the dimension actually never features. Even though it features in the propagator, like in the Donner gauge propagator, there's an explicit D, but it's actually not there when you compute the 3-level amplitude. It just disappears. Yeah. Well, you pick the same helicities for these 2 factors, yes. And you could pick opposite helicities, and then you would get a scalar instead, or 2 scalars, in fact. And that's something different, which I wasn't planning of talking on right now, I think. Yes, but I will talk about it later, I guess, yeah. But yeah. Okay, how am I doing on time? Am I out of time? No. Half an hour, okay. Okay, so I guess one thing I wanted to say is that we typically talk about this double copy map, which also is just, we call it double copy. Double copy. Okay, where did I lost it. Yeah, so basically, it's essentially just a product. So, essentially, you can just think of it like, given that we have 2 amplitudes of this form, the double copy is simply taking these 2 amplitudes and merging them, removing the color factors, right? Right. Yeah, I'm just trying to make it a slightly more formal, right? That you have two objects. That you define a map such that the output is this, right? And then we do it schematically, or maybe not schematically. We do it more generally, and we talk about not just amplitudes, but we talk about the theories themselves. So we talk about a gauge theory. Times a gauge theory. Right? And this gives a gravity theory. So you can either interpret this equation as a schematic equation, or you can just interpret this as saying, for any amplitude, there's a map that gives this as an output, and this is basically what this is incorporating, right? And I'm just mentioning that because later on I will write this equation several times, and then you might wonder, what does it mean? It just means that you should be able to feed it through this map and get an output. Yeah, what's the question? Can you speak a bit louder? The color? Yeah, I put a different color factor. I mean, it doesn't really matter. It will drop out of the map. As long as this color factor has the same algebraic properties as this guy, which it should. I mean, they should have the same Jacobi identities. But of course, if you have different representations of the gauge group, you want to make sure that there's some kind of correspondence between these representations. But in general, the gauge groups can be different. It doesn't really matter. Okay, good. So now I'm going to talk about KLT, which is actually the origin of the double copy, in the sense that it was discovered there first. So KLT, which stands for Kawai, Llewellyn, and Tai. And they discovered this in 1986, I think, or maybe 85. I think paper was published 86. So it turns out this double copy formula can be re-expressed. So let's write it down again. And it goes from 1 to 2n minus 5 double factorial. So what we can do here is we can now put both numerators in this DDM basis. So this n minus 2 factorial basis. And then we get a sum, sigma and rho, which belongs to this basis. So they both belong to Sn minus 2. And then we have the numerator 1, sigma, n. And then we have m, sigma, rho, and twiddle 1, rho, n. And I have to apologize for the many n's which are different here. Okay, so this is not yet KLT, but it's in the direction of KLT. So KLT is actually a map of the form that I wrote there. It's basically a map between amplitudes, partial amplitudes. And we can actually see the partial amplitudes. I don't know if I wrote it down. I think I wrote down the partial amplitudes before. I think I have erased it. But we can see that the partial amplitudes are actually sitting here. So for example, this thing here is actually the partial amplitude. This is a 1, rho, n. And this thing here is also a partial amplitude. This is a twiddle, because it depends on n twiddle, 1 sigma n. So you see the partial amplitude is sitting here, but they're kind of using this propagator matrix twice. So what you can do then is that you can basically multiply and divide by this propagator matrix such that you get 2 copies of it. And then that gives you a different formula, which looks like, well, it's a sum over sigma and rho, A1. And I said you have to multiply and divide, which means that you have to take the matrix inverse. But I said before, it has no inverse. So you're a bit in trouble. But you can do a pseudo inverse. So that's what I'm going to do here. And the pseudo inverse I'm going to call S. And I also changed, I don't know, yeah. For simplicity, I changed the ordering here, which I can always do by some Kleist-Coif relations. Yeah, so this is, as I said, is basically, well, this is called the KLT kernel. It's a matrix. And in fact, the KLT kernel is the pseudo inverse of this other matrix. So let me write it over here. S rho sigma is the pseudo inverse of this propagator matrix M sigma rho. Let me not write down a formula for it, because you might know that pseudo inverses are not that well defined. That means that there are many of them. But I guess the point is that if you multiply the pseudo inverse with the thing you're trying to invert, then you get identity, right? So that's the definition. And I'm kind of presenting it in a backwards way, of course, because KLT basically did this work in '86, although they didn't actually write down this KLT kernel for general multiplicity. That was actually done later, much later. But it was still written, this was still written down before this was written down. And I didn't give you a formula for the propagator matrix. I just gave you an example. And that's because the formula is a bit involved. I think there is a formula in literature or something along that lines, but essentially implies that you have to use some kind of recursion. But it turns out that this inverse, the KLT kernel has a closed formula, so let me give it. So it's a product of things, let's say from 2 to n minus 2, and then it's 2 p1 dot p rho I plus sum over j equals to 1, sorry, equals to 2 to I to p rho I dot p rho j, and then there's some function that people call theta, which depends on sigma, and also on rho I, rho j. And this function theta is just equal to 1 or 0. And it's 1 if this permutation sigma of rho if sigma of rho is larger than sigma of rho j, so for the different particles, and 0 otherwise. So essentially, it just compares, like if you have two different orderings, sigma and rho, it just compares the orderings, like which one is bigger than that, which one comes before the other one. Roughly, that's what it's doing. But it's a relatively simple formula. And there's also, you can also define it recursively, then it becomes even simpler, but I'm just going to give that formula. Was there a question? Yeah. A sign? You mean here, or I don't know? Well, there. Oh, you mean a sinus function? That's what you mean. Oh, okay. Now this is the field theory KLT. Yeah. I don't. Yeah. So there's many different KLT kernels. This is not the only one. Because pseudo-inverse, there's many solutions to pseudo-inverse. So this is one particular one. I think this is the sort of the standard one. But then there are other choices. And some of those choices you can then directly promote to the string KLT by just putting a sign function. Like every time you see a dot product here, you just put sign of the dot product. I think not every KLT formula can be done that way, because obviously you can take linear combinations of these SIJs or dot products, but that doesn't work for, if they're inside an argument. Anyhow, yeah, so when I talk about KLT, I always talk about the field theory limit of KLT. It was originally, of course, obtained in string theory, but these days people mostly use it for field theory, and not so often for string theory. Yes? Yeah. Basis? Yeah, so actually I didn't say here, but there's a basis change here. This is S n minus 3. This is the permutations group of n minus 3 elements, yeah? Yes, the reason is because this matrix is degenerate, and that means that at best I can actually just look at the non-degenerate elements, which is n minus 3, and I can sort of invert those elements. But I, and that's essentially what's going on here, right? I have inverted a subspace of that matrix, and that gives this inverse, right? Yeah. Yeah. I didn't show the intermediate steps here, but I sort of hope that you can kind of see what's going on. Yeah. Any other questions? So let me give you some formulas. This might be a bit too cryptic, so I'll give some examples. So M at 3 point, I guess maybe it should be curly M, whatever. So let's also put this kappa over 2. I think I put the kappa somewhere, but I might have erased it. Actually, people usually put kappa over 2, and kappa is essentially the coupling constant of gravity is related to the square root of Newton's constant with some factors of pi and so on. So if we want to do 3 points, you have to multiply 2 different orderings. Well, there is basically just one ordering at 3 points. So this is what David showed, I think, already yesterday, that you essentially just square your 3-point amplitude. But I put a tilde here in case you want to consider different theories or different states. It also holds if you have different states. And then there's M4, also kappa over 2 squared. And there's an S12, which is coming from here. And then A 1, 2, 3, 4. And then you have to now change the ordering here. So it's going to be 1, 2, 4, 3. And you see that it's n minus 3 there, which is 3. So we're sort of going outside of the conventional DDM basis here. on this side we stay in the DDM basis, but here we sort of picked a different DDM basis. And 5 point, that's the last one I'm going to write down because it's getting a bit complicated. So S1, 2, S4, 5, A, 1, 2, 3, 4, 5, A, 1, 3, 5, 4, 2, and then there's one more term, which is S, so plus S, 1, 4, S, 2, 5, A, 1, 4, 3, 2, 5, A, 1, 3, 5, 2, 4. So that's basically 2 terms of 5 point. And that's what I was referring to before, is that if you compute a 4-point amplitude, it will always factorize, pretty much no matter how you do it. But at 5 point, you're going to have some trouble to see that it factorizes because it's a sum of 2 factors. And so this is going to be hard to realize unless you know exactly how to split it up. And these SIJs are just the Mendes terms. SIJ is PI plus PJ squared. Generalized Mendes variables. So that's a very nice exercise, but I don't think I'm going to assign it as a homework unless you really want to do it. But let me mention it. So just compute the GR 4-point amplitude from the Feynman rules of Einstein-Hilbert action. Do it any way you like, but it's important that you need to write your polarization like this. So do that computation in Mathematica, and then you hit full simplify, and it will give you that it factorizes into 2 factors. It's a very cool exercise, because before you hit full simplify, you have a monster, like it's an incredible monster, and then you hit full simplify, and it becomes extremely simple. Okay, let's see, how am I doing on time? 10 minutes, I guess, yeah. Okay, so let's talk a little bit about this contamination. So I was saying that there could be matter, and somebody was asking, you were asking me about whether you can pick different helicities here, and you can. So let's talk about the states. Let's do it over here. All right. Indicate, I think this is the best you can do, I think, yeah. I think so, yeah. Yeah, so you can, no, I don't know. But I think at some point I looked at, what I did is I looked at other versions of KLT, which comes from different pseudo-inverses, and they were always worse than this one, yeah. There might be other ones which have the same number of terms, but they are roughly the same. I guess I erased my general formula, but I think the key is that there's some kind of halfway split, like you treat half of the particle one way, half the other one, but of course halfway is ambiguous if you have an odd number, so that's why there's like 2 formulas or something like that, yeah. Yeah. Say again, what? No, I mean, you might say, yeah, the rank was 1 here, so there's 1 term, and the rank was 2 here, so there's 2 terms, so there's a pattern, but I think that's just that's an accident, I think. Well, I don't know, or maybe you should count, maybe I'm wrong, maybe it is the same, but it doesn't, I mean, the point is that it doesn't follow, because if you did a different KLT formula for a different pseudo-inverse, it would get worse. Yeah. Okay, so you're saying the best option is where the number of turn matches the rank? Maybe. Maybe. Somebody should check that. That's the homework. Okay, good. Okay, so now I want to talk about the states. So what are the states in the double copy? Let's say now we're going to be specific. So let's talk about the specific theory. Yang-Mills times Yang-Mills. And what I mean pure Yang-Mills. So we know that this should be GR, but there might be some plus, dot, dot, dot. And so let's talk about the graviton first. So the graviton, which we often call h mu nu, or let's put the mu nu upstairs. It doesn't really matter. And so as I said, we use that formula. Basically, we write down two polarization vectors. And then I said it's very good if you use null vectors, because then it just factorizes. But you can also not use null vectors. That's also okay. But then you better also keep track of the little group indices. So in principle, there should be some little group indices. Let me take one step backwards. So here's our polarization tensor, and then we put some little group indices. So let me just remind you that the little group is SO D minus 2. And don't ask me questions about the non-compact part. I'm just going to consider it compact, just the rotations. So basically, ij here is going to run from 1 to d minus 2. All right, so I'm just going to factorize it. But of course, in general, you cannot factorize a rank 2 matrix. But with these indices here, you can basically say that there's a one-to-one map for each little group index. And what you have to do here is you have to symmetrize these guys, which I denote by this bracket. But you also have to subtract the trace. So that's usually people denote by a second bracket. So symmetric and traceless. And then you can count how many states there are. So there are d minus 1, d minus 2 over 2 minus 1. So this is just from a symmetric matrix, and that's subtracting the trace. But then there's also a 2 form. There's a 2 form b mu nu. So that you can just also represent by a polarization. Tensor. I don't know what the usual convention is, but let me just put a tilde. It's not the same thing as that guy. Also has some little group indices. So also has the same formula. But now you have to antisymmetrize your indices. So it's basically just antisymmetric. And how many entries are there? An antisymmetric matrix in the little group is basically a d minus 2, d minus 3 over 2. Okay, and then finally there's a scalar that we often call dilaton. Phi. And we can also represent that by polarization tensor, even though it's a bit weird. Yeah, I'm not sure. Double tilde, I guess. All right, let's put just a subscript phi to make sure that this is the dilaton. So this one you can write as epsilon I, epsilon j, mu nu, And then you contract this with a Kronecker delta. So contract AJ with a Kronecker delta, and then you have to normalize it correctly, which is usually done with d minus 2 in the denominator. And there's one such state. And then you can add up. You can add up the number of states, and of course it's going to give you total d minus 2 squared, because it's just the squared states of Yang-Mills. In Yang-Mills you have d minus 2 states in the little group, and you get the square. You could have also done this with null vectors, which I was talking about here. For example, in 4 dimensions, it's very convenient, but you can actually also do it in other dimensions with null vectors, if you think a bit about it. But I'm not going to do that. Okay. Yes. Maybe in the last -1 minute, I'll write what is the theory, because the Lagrangian is actually known. So, well, let's talk about the action, I guess. Action of Yang-Mills times Yang-Mills. And this, of course, is just done by matching. It's not something you can just work out from anything we have done. You have to just do the matching carefully. And I'm not the one that did it. This was done a long time ago in string theory, because it's the same Lagrangian that appears in string theory at low energy. Is it a 6? I think it's a 6. E to the minus 4 phi d minus 2, and then h mu rho squared. Okay, there we go. So is the Einstein-Hilbert term? I guess I've set kappa to 1. 0. Yeah, I set kappa to 1. So the Einstein-Hilbert term is a kinetic term for the dilaton. And this square, of course, means that you contract with the metric. I just didn't write like that. And then there is basically like a kinetic term for the B field. So it's a field strength for the B field, which is essentially just d mu h rho sigma, and then you antisymmetrize, and then there's some numerical factor maybe, but that's the field strength. And there's some weird dilaton warp factor over here. But that's a well-known Lagrangian. It's the same Lagrangian that appears in string theory. In string theory, you would either set this to be 10 or 26, but here you get it in generic dimension, I guess. And you can see that something weird happens if you go to 2 dimensions. And the weird thing that happens is that the dilaton basically disappears. Yeah. Is that exact? Oh, you mean if there's other terms here? I believe I believe this is correct. If you have vectors in your theory, then you have to correct it. But if you have no vectors, then the field strength is just abelian. This is a abelian field strength, yeah. Yeah. Yeah, there's there's only one tensor, so it's an abelian tensor, yeah. Well, nobody knows what non-abelian tensor is anyhow. Yeah. Yeah. That's right. That's an equality. Yes. Yes. Oh, sorry. Yes, sorry. Yes, thanks. It's a B. Sorry. Yes. Thanks. Okay, good. Any other questions about my notation? All right. Otherwise, that was what I was going to say today. So yeah, thank you.
Well, I guess there have been lots of questions already, but in case you have still more questions before the coffee break. Otherwise, we can save it for the discussion session. Okay, and let's thank Henrik again.